All right, so let's get started, guys. And first of all, thank you for joining in. Thanks for being a part of this class. We have a huge class this time, almost 80 students, probably more. So I'm sure that EAs and UPIs will get a hard time. Right? But yeah, we have one of the TAs with us, Michael. He took this class last year with me. So you guys can say hello to Michael. He will be helping you guys with most of the labs and maybe some of the homeworks as well. So please feel free to reach out to me or any of the TAs or UPIs during the semester. We are always there to help you if you have any trouble with any of the material or anything related to this course. All right. Now, of course, today is the first day of the lecture, and the first day is always the most important. So you have to figure out whether you like the instructor, whether you like your peers, whether you like the TAs. Where are you going to sit for the rest of the semester? Is it the first bench, the last bench, or somewhere in the middle? So I kind of told this last year as well, but what worked for me throughout the years is that sitting in the middle, because if you're sitting in the first bench, you are right in front of the instructor, sitting in the last bench, the instructor might sometimes look at you, what are you doing, and whether you are paying attention to the class or not. So what worked best for me is sitting in the middle. So you can really hide and not be part of anything interesting. All right, so jokes apart, this is EEE 3308C, and we're going to learn about electronic circuits. So some of you already have very fundamental or basic ideas about electrical circuits, because some of you have taken the, I guess, 3111. That's the course, that's a prerequisite of this class. But what are we going to learn in this particular course is more about electronic circuits. And why is it important? Because if you look into any of the devices that you are using today, be it your laptop, be it your smartphone, smartwatch, or any other device that you are using today, it uses all these electrical and electronic circuits that we're going to learn in this class. And of course, you'll know that today, with the advent of ChatGPT and all these AI-based technologies, writing code is something that even the chatbot could do. But if you're learning something about real electrical hardware or electronics, that is a skill that today the ChatGPT cannot do. Maybe 10 years down the line, it will be able to, but you're safe till that point. And I'm assuming that you'll learn enough skill in this class so that it can get you through those 10, 15 years, and within that time, you'll learn more skills so that you stay relevant, right? So that's the hope. Now, and I'm hoping the same too, because I'm only skilled in this. I cannot write code. So yeah, I guess again, I'm telling too many jokes at this point, but I guess it's important as this is the first class. Now, there are a few information which would be relevant to you, and everything is provided in this Canvas page. So please note, of course, all of you are here, so I think you have already noted the change in the class location. There is also a change in the lab location, so it will be in MAE-B 226, and it is provided in your syllabus. So if I just go into the PDF, and the important parts are already highlighted over here. So one of them is that the labs will be held in MAE-B 226, and that is an updated location. I think in 1.uf you previously had a different location for the labs. The times and sections are as per your Canvas schedule or 1.uf schedule. All right. Okay, now coming back to the Canvas page. So first of all, again, thank you for joining in the GroupMe link. So here we will be discussing many of the technical as well as non-technical stuff related to the class, announcements, and so on. So please join the GroupMe link if you haven't done that already. The syllabus is also provided here. We'll go through that in a bit. But more importantly, this class has a lab section, as you already know. And for the lab, you'll have to order a few parts. It's not very expensive. It probably costs around $20 or so overall. But please go through the parts list, and I'll discuss the individual parts in a moment. But some of these parts might take a few weeks to arrive, so please be proactive in ordering the parts, because the labs are going to start in about 2 weeks. And I've also provided a tentative date for this. And I'm hoping that all of you will have your parts ready by September 6th. That's 2 weeks from now. And for the first 2 weeks, there is no lab. So that's one announcement I wanted to make here. Lab schedule, again, the same as have been provided in your 1.uf or in your Canvas page. And this basically talks about the 7 labs we'll be having throughout the semester. Please also look into the TA/UPI office hours. So Troy, who will be the TA for this class, he has already provided an office hour Tuesdays and Thursdays, 10:30 a.m. to 12 noon. And I have my own office hours every Wednesday after the class from 12 noon to 1 p.m. at NV 533. And you can also join in using a Zoom link, which I also have for the class if you're not able to be present in person. All right, and I'll be uploading all the lecture notes and handouts here. So for example, if you look into it, lecture 1 and lecture 2, which is today and Friday, we already have the lectures uploaded over here. And similarly, the lab notes and handouts will be uploaded on this Canvas homepage itself. Any questions? All right, if not, maybe I can go over the syllabus and the course structure a little bit, and then we can go ahead with the other logistics. Okay, so again, this is 3208C. Please note the updated location as well as the updated lab venue. Office hours are mentioned here, as well as the contact details of the UPIs and TAs. The UPIs will mostly be helping you with the labs. The TAs will be helping you with the homeworks and other stuff related to the course. All right. So what are we going to learn in this course? What are the main themes? So the main theme in this course is how to design practical electronic circuits. And how do you design circuits that do useful things? What is there inside your smartphone? What is there inside your laptop? So you'll, of course, not be able to learn everything, but I'll try to give you an idea or a gist of what is there inside these electronic devices that you are using today. And for that, we'll be learning about a few basic electronic elements, and we'll be using a basic fundamental laws of electronic circuit theory, including Ohm's law, Kirchhoff's laws, Thevenin's and Norton's laws, and so on. We'll also learn about diodes, we'll learn about MOSFETs, and we'll discuss significantly about MOSFET-based circuits, because that's what you have in today's CMOS-based technology. So some of you may already know this, but most of the devices that you're using today are based on CMOS. That's a silicon-based technology with complementary NMOS and PMOS. We'll discuss all those details later on. So don't worry if you don't know about NMOS and PMOS at this point. And most importantly, we'll be doing design-oriented analysis throughout the course. And what we mean by design-oriented analysis, that will emphasize most on what are we trying to design. Will not emphasize on the mathematics of it. So for example, you can derive an equation or you can solve an equation to find out, okay, the value of X is probably 99.995678, something like that. So you don't want that in this course. As long as you say that X is almost equal to 100, it should be good. And why is that? Because you know that all electronic devices have some tolerance. So if you have experience with working in electronic labs, you'll know that if you are experimenting with a 100 kilo ohm resistor, for example, if you have a resistance of 100 kilo ohm, it may not be exactly 100 kilo ohm. It could be 101, it could be 95, it could be 104. And that's the tolerance level that you usually have in any electronic component. What does that mean? That if you're mathematically calculating what would have been your final output, assuming that you have an exact 100 kilo ohm resistance, you may not end up with that exact same value in measurements or in practicality, right? So if you can never have the exact value in a practical application, what's the point of doing an exact mathematical calculation? Right? You don't have any point. So that's why we are going to do a more design-oriented analysis. That what does the design require? How would the changes in the component values affect your final design? Or what are the steps that you need to take to make sure that your final design works, even in the presence of these variabilities or non-idealities? That is something we are going to emphasize on, and will not emphasize on the exact mathematical result that you might find by doing a calculation. Right? So that's what I'm calling design-oriented analysis. All right. So the tentative syllabus is also provided here, and of course we may or may not be able to follow this to the dot. But if you look into it, in the beginning we are going to start with very fundamentals. So we are going to discuss Ohm's law, KCL, KVL, voltage or current dividers, and we'll give a introduction to op amps or operational amplifiers, which is a very important circuit construct that people use in all practical electronic circuits. We'll discuss the ideal versus non-idealities of these op-amps and different ways that you can use op-amp circuits or how to build different op-amp circuits. That's also something that we'll be discussing over the next few lectures. We'll also look into the frequency response of different electronic circuits. That what does that mean? That, for example, let's say you're building an audio amplifier. And for an audio amplifier, it is sufficient to work with frequencies up to, let's say, 20 kilohertz or so, maybe a little higher. You can go up to 50 or 100 kilohertz. But how would that device or how would that circuit behave if you go to higher frequencies? That is something is very interesting to analyze and to look at. So that's why we are going to look into the frequency response of different circuits. We'll be looking into diodes, BJTs or bipolar junction transistors, and MOSFETs or metal oxide semiconductor-based field effect transistors. And we'll be looking into many different variations of designing circuits with MOSFETs. In between, I have also noted down the holidays where we'll have no classes. And this course will have 3 tests, in-class tests. The first of which will be on September 22nd. The second one is October 25th. And the third one will be December 4th. So those are the 3 tests, again, tentative, but last year, we kind of followed what we had in the syllabus already. So I'm assuming that there will be no issue with having these tests in class and on the respective dates. Yes, question. Okay, yeah. So the tests will be in class, and again, there will be 3 tests throughout the semester. No final exam. The last test, the test number 3, that's something you can assume as the final exam for this course. Okay, because we understand that during the second week of December, you might be busy with other courses, other exams, and so on. So we didn't want to burden you with all of that. The last test will be on December 4th for this class. Also, as you already might have noted, that there are 7 labs that you need to do. And these labs, for example, the first one is just an introduction to electronics. You'll be learning about Thevenin's theorems, Norton's theorems, and so on. You'll be looking into non-ideal op-amps. You'll be looking into diodes, MOSFETs, and many different applications of MOSFETs and BJTs. And finally, we'll also look into CMOS logic. So we already talked about it, that your phone or your laptop uses CMOS logic. So what is CMOS logic and how we can build circuits with CMOS logic? That is also something that we're going to learn in this particular course toward the end. All right. So materials, of course, you'll need the DAD board, and I hope all of you, or at least most of you, already have access to that. And we need a few parts which you'll need to order, and it's provided in your Canvas page. So these are the parts that you need to order. So we'll need a few op-amps, and as well as other components like MOSFETs, diodes, BJTs, and so on. So most of these components are pretty cheap. They cost about $1 to $2, maybe $3 per component. And I have provided a link to a DigiKey page. I want to do that. So yeah, it might take some time to come up, but it already have all the components added, so you can just go ahead and order. But if you would like to search more and find components at a cheaper price in other websites, you can also do that. There are we have provided some advice on ordering the components. So there is something called Octopart, and here you can compare and find out different devices and components. So for example, for this CA3130 op-amp, So I'd like to sort of give you some information on this, that this op-amp was not available last year for most of the semester, but this year I think it's available again. But it might not be available in enough quantities. So for example, let's say this Future Electronics has only 45 of them, although Avnet has 2000 and Funnel has around 153. That's what you're seeing from this Octopart website. So please go ahead and order these components, especially the CA3130 op-amp, because this might go out of stock soon. Okay, so please be aware of that. But excuse me, but we have also given you a few alternatives. So for example, what we need is the CA3130EZ, which is a dual inline package or DIP package, which you can put on a breadboard and work with that. But if the DIP package is unavailable, Mouser or DigiKey, both of them has a lot of CA3130MZ, which is a SOIC8 package. So it looks a little different, but it works the same. So you can order that component as well, but it needs to be mounted on a socket so that you can place it on a breadboard. So this is a SMD component or a surface mount component. So if you just look into it, you'll see that it looks a little different. Let me show you. Yeah, so this is the component we need to order, and it is something that you probably have already worked with, or similar ICs that you have probably worked with, that you can put this on a breadboard and do your experiments. But on the other hand, if I open up this, you'll see that this is not available right now in Mouser. But on the other hand, this package is available, which is a little different from this. You cannot use it on a breadboard. So what you need to do is that you need to order a socket that you can place on a breadboard and put the device on top. So that's just an alternative if you cannot find the DIP package. But I'm sure that as I have mentioned here, that in Octopart you see that there are multiple vendors who have this device in stock. So please go ahead and order it as soon as possible, because it may go out of stock in a week or so. All right. So that's about the parts list. So please be a little proactive. Let's try to order it within this week if possible. And I have provided all the links and everything so that you can directly go into these particular links and start ordering the components. Okay. So other things about the syllabus. The textbook that I would like to refer here is from Behzad Razavi. He's a professor at UCLA, and he has this book on fundamentals of microelectronics. I provided the ISBN numbers as well as an Amazon link, but digital copy is also fine if you're able to find one. But if you don't have this book, or if you cannot have access to this book, you can also refer to Sedgwick and Smith, which is again a very similar in terms of all the concepts that is discussed in this book. But I'd like to mention here that the Sedgwick-Smith book is kind of a little outdated. For example, they use voltage levels such as 10 volts or 15 volts, which you would not find in today's electronic circuit. So today's electronic circuits mostly are using 5 volt or 3.3 volt supplies, right? If you have worked with a microcontroller or any other electronic component before, you'll know this. Yes, question. It can be an older one as well. So the 3rd edition is the latest one. So I just mentioned it here. But if you have an older one, that should also work. So what's interesting about the textbook that I am recommending is that it is more updated. And for example, you have the supply levels as 5 volts or 3.3 volts in all the problems that will be covered in this book. On the other hand, Sedgwick-Smith works mostly with 10 volts or higher supply voltages and circuit components which are a little outdated, I would say. But along with that, I'll provide material on Canvas for each lecture and lab. So for example, for today's lecture and Friday's lecture, I have already uploaded a presentation that we are going to discuss today and on Friday. But yeah, I mean, in a similar way, I'll be providing you material throughout the semester. The Evaluation and grades are mentioned here. So we have 10 homeworks. Each one of them will be 100 marks each, but we'll be taking the best 9 out of those 10, and we'll drop the lowest grade because I understand because this is throughout the semester, and it is possible that for one of the homeworks you are not available or you may not be doing as well in all the 10 homeworks. So that's why you are going to drop the lowest grade. We'll be considering the best 9 out of 10, and that will constitute 18% of your overall grades, 2% each. There are 7 labs, again 4% each, that will constitute a total of 28%, and 3 exams will constitute 18% each, that will give you a total of 100. The grading policy is very similar to what you usually have in US, and there's nothing new in this. Labs, of course, this is very important. It will be done similarly to your 3701 class if you have taken that. You will be provided a lab manual before each of the labs, that's what you need to do in that particular section or that particular day. And of course, your EPIs will be available to help you out with any questions or any trouble that you have with the lab. But you are expected to understand the lab manual, analyze and build the circuit. So there will be a pre-lab section and there will be an in-lab section. The pre-lab section means that you have to do some amount of calculation or analysis for the circuits that you'll be designing in lab, and you'll have to keep it ready before the lab starts. And there will be an in-lab section, which would be the second part that you need to perform in the lab. Now, of course, I think the pre-lab section constitutes of 80% of the total grade in that particular lab, and the in-lab section is 20%. So you have to be careful what you are doing in the pre-lab section, because that's something you're going to repeat in the in-lab. All right. So just look into all the material that have been provided already in terms of the syllabus and the first few lectures, and it should be good to get started with it. Homeworks, it's usually about 1 per week, but some weeks will not have homeworks. As you know that we have 10 homeworks in total, but we have more than 10 weeks in this course. But keep in mind that there could be homeworks every week. And I'll be assigning the homeworks on a Friday, and it will be due by the class start time on next Friday. You can upload it on Canvas directly in a PDF format. All right. Now, how to study for this course is that all the exams and you'll see even the labs will deal with design problems. So we'll be providing a lot of examples in the class, but try to solve as many problems as you can from the textbook or from the reference material that I will be providing. And then you should be good with all the exams or at least with the preparation part of all the exams and labs. So try to solve as many problems as you can from the book or from the material that we'll be providing. And that's kind of the expectation from this particular class. All right, so I'm skipping all the other things which are kind of common to all the classes that you're taking. And any questions at this point? All right, if not, let's get started. And the first few slides I have already covered. So it talks about my office hours, the TA's office hours and availabilities, as well as the organization of the class and the recommended materials, textbook, everything we have covered from the syllabus itself. You also have the evaluation of grades and the grading policy uploaded here, as well as the syllabus. So you can also refer to this document directly, which is just a copy of the syllabus at this point. All right, so a little bit of background about myself. So let me see if I can, yeah. Okay, my name is Boibhav Chatterjee, and I'm an assistant professor in the Department of ECE. I joined last year in fall 2022. So I'm also fairly new to the campus. It's been only a year. I taught this course last year as well. And we talked about or discussed mostly similar things that you see in the syllabus that I presented today. Now, I finished my PhD last year from Purdue University in 2022. And the research work that I had done and I'm still doing, I'm continuing some of those work is related to something called human body communication or HBC. And you'll see that many of the components or constructs that we'll be discussing in the class are applicable to the research work that I do in my day-to-day life. And what is the exact research we're trying to do is, you know that the human body is conductive. So we all get shocks in winter, or it's possible to conduct electricity through the body. Now we are using this property that the tissue is conductive or the human body is conductive to send signals through the body. What kind of signals? For example, let's say we are meeting for the first time today. And I'm just giving out an example. It will not happen right now. But if we are, let's say, just shaking hands, you can send a LinkedIn invitation to me just by shaking hands. Because your smartwatch can have that information that, okay, you want to send a LinkedIn invitation or a LinkedIn invite, and I'll get that information in my smartwatch. And that can be established just by shaking hands, because by shaking hands, you're establishing the link between two human bodies, and the signal can pass through the body. Okay? So those are the kind of cool technologies that we are working on, and it does not end there. It does not end by sending a LinkedIn invitation. You can also do other things. For example, sending high-speed video and audio through the body. You can use it on patients for, let's say, medical implants, where today people are doing wireless Bluetooth technologies. So people are using wireless technologies to send data from an implant or from an wearable. But traditional wireless is pretty costly in terms of the power consumption, and also the security level is not as good. So we are trying to improve the security as well as the power or energy consumption of these devices by sending the data through the human body instead of sending the data through air using traditional wireless communication. So that's one part of my research. So if you guys are interested in talking more about any research opportunities for undergrads, I'll be happy to talk to you about some of these details. All right. So now what are we going to learn in this particular course? And I have already talked to you briefly regarding this, that we are mostly going to do a design-oriented analysis. We'll keep in mind that designing the circuit and analyzing it approximately is our one of the main goals. And why that is important? Because as we already talked about, that electronic components always have tolerance. So there's no point getting the result up to the 5th decimal point or something. All the companies, so if you're interning with TI or working in TI or analog devices, or even today Google, Meta, Microsoft, Intel, all of them has hardware groups. So if you're working in some of those groups or interning in some of those groups, they will be expecting you to analyze the circuit within a quick amount of time, within a short amount of time. So they would want you to analyze the circuit quickly. They don't want you to get to the result with 5 decimal places accuracy. And that is something we are going to learn and practice in this course, that how to analyze circuit quickly. Calculations, anyone can do that. Even ChatGPT could be able to, like, I know that it does not do calculations that well today, but it will be able to in a few days or in a few years. So we are not interested in doing that 5th decimal place calculation. We are interested in analyzing the circuits quickly, and we'll learn ways to do that throughout this course. Now, there are a lot of ways to analyze circuits. You can, and some of these methods you already know if you have taken 3111. So some of these methods include nodal analysis, loop analysis, or mesh-based analysis, and so on. And you can do any of these, or you can resort to any of these analysis techniques, and they will give you almost the same answer for each of the problems that you are solving. And applying any of these techniques is okay. You just need to sort of figure out that for a particular problem, what type of analysis gives you the answer in the quickest manner. Right? So that will be something we'll practice a lot in this particular course. Now, what we'll start with will be something called voltage divisions, current divisions, parallel and series equivalent circuits, as well as Thevenin's and Norton's theorems. That is something we're going to analyze and look at in the first few lectures, which are just tools that you'll be using throughout this course to analyze different circuits. So first of all, we're going to start with Ohm's law, and I'm hoping all of you know what Ohm's law is, and it's a very basics of any electrical circuit. And it states that if you have a voltage of V across a resistance of R, the current that will be flowing through that resistance will be equal to I, and I will be equal to V over R. So that's just a linear equation that you have, and that's called the Ohm's law. And along with that, we'll be using Kirchhoff's current law and Kirchhoff's voltage law. So what does Kirchhoff's current law states, or KCL states, is that if you have a lot of different currents coming into one particular point in your circuit, so currents can flow from point A to point B, right? So that's how electronic circuits or devices work. Now, if you have many different currents coming in from different directions to one single node, the overall combination of currents or the addition of all those currents will be equal to 0. Because you cannot create or destroy current, just like you cannot create or destroy energy. It's kind of an equivalent or analogous to that statement that the summation of all the currents will be equal to 0 if you're applying KCL in this particular node. So for example, here you have current I1 coming through this direction, I2, I3, I4, and I5. So I1 and I2 are coming into this node, and I3, I4, and I5 are going out. So applying KCL, how would you write it mathematically, is something like this, that I1 plus I2 will be equal to I3 plus I4 plus I5, or another way of writing it is that I1 plus I2 minus I3 minus I4 minus I5, that will be equal to 0. So that's what Kirchhoff's current law states. Similarly, there is a voltage law, which states that if you have a loop, an electrical loop, consisting of many different components, there could be resistances, capacitances, inductances, and so on. In this case, we are showing just resistors here. In this particular loop, the overall voltage is equal to 0. Again, what that means is that if you have a voltage source, the voltage source will create some amount of current in this loop, right? And that current, when that flows through these resistances, will create voltages across these resistances according to Ohm's law. So Ohm's law says V equal to IR, right? Or I equal to V divided by R. So you'll develop a voltage of V1 across this resistance as the current passes through the resistor. You'll develop a voltage of V2 across this resistance as the current passes through it. What Kirchhoff's voltage law or KVL states is the summation of these three voltages. One is a source voltage, and one is these two voltages which are developed across the resistors as a result of the current flow through the loop. The summation of these three voltages are again equal to 0. And just to make sure that you have, in this case, you have a voltage source. So this particular construct is a voltage source, whereas this is where the voltages are getting dropped, right? So we call a voltage drop, that you have a voltage drop of V1 across this resistor and a voltage drop across the V2 across the other resistor. So why there is a minus sign? It's because that you want to sort of emphasize on the fact that V1 and V2 are the voltage drop, whereas this V is basically a voltage source. So something is sourcing the voltage and something is sinking the voltage, or basically something is using that voltage to develop this V1 and V2 across the two resistors. So just to make sure that you have a distinction between the source of the voltage and the sink, or in this case, you generally call source and sink in terms of current, but I just wanted to make sure that we are emphasizing on the fact that one is a source, whereas the other ones are not source. They are developing the voltage because of the current flow through them. So that's why there is a the signs or the magnitudes are different for V, V1, and V2. Okay. Questions? All right. So next, we'll be discussing a little bit about voltage divisions, that how do you analyze circuits when there are multiple of these resistors. So this is again one example that you have a voltage source of Vi or V input, and you have two resistances, RA and RB. So resistance A and resistance B. So what would be the current flowing through this entire loop? So again, there is a loop that you have created here. The current flowing through this loop will be the total amount of voltage in this loop, the source voltage in this loop, divided by the total amount of resistance in this loop. And that's again Ohm's law. So current equal to voltage divided by resistance. So your current flowing through this loop is voltage divided by RA plus RB. And of course, if you are trying to find out the voltage at any point, let's say we call it V output or VO. So let's say if this is the voltage that we are trying to find out here, what would be the value of VO? If you assuming that this point is grounded, or you have a reference point in the overall loop, which is connected to the negative input of the voltage source. In that case, this VO is the voltage between this point, the top terminal of RB, and the ground. So that's the output voltage that you want to calculate. So this output voltage will basically be the current that is flowing through the resistance RB multiplied with the resistance value. So again, Ohm's law. So your output voltage is current multiplied with RB. So you're just applying Ohm's law here. You applied Ohm's law here on top to find out what is the current flowing through the loop. And then you are applying Ohm's law again to find out what is the voltage across RB. So the voltage across RB is I multiplied with RB. That gives you VI times RB divided by RA plus RB. Right? Because VI divided by RA plus RB, this part of the equation was your current. Okay. So this is a voltage division when you have two resistors in series. And two resistors in series, they will be divided in proportional to their resistor values. So if you see here, this is something interesting that you're trying to find out the voltage across RB. What is V0? V0 is basically the voltage developed across RB. And that voltage is proportional to the resistor itself. So V0, or the voltage developed across RB, you can call it VRB or VB itself. And VB or VRB will be proportional to the value of the resistance. Similarly, if you wanted to find out the voltage drop across RA, let's say you want to find out what is the voltage drop across the top resistance RA, and let's call it VA, the drop across the resistance RA. That would again be the current flowing through the loop multiplied with RA, correct? You already know what is the current flowing through the loop, that is this equation, and you multiply that with RA. So something interesting to note here is that voltages developed across RA and RB are proportional to the value of RA and RB. So that's true for this voltage division in two series resistors. Okay. Similarly, you can think about a current division in two parallel resistors. In the previous case where you have two series resistors, you did not have a current division. There was one single current flowing through the loop, right? This is the current flowing through the loop. But if you had two parallel resistors, the current will be divided. So if you have this current as the initial current I input, that current will be divided into two parts. One current will flow through RA, the other current will flow through RB. So when you have two parallel resistors or two parallel impedances, the current gets divided into two parts. If there are three resistors, the current will be divided into three parts, and so on. Now, how do you find out what is the current division here in RA and RB? You have this input as II or I input. That's the current that you are providing at this point, at this node, and then that current is getting divided into two parts. One flows to RA and the other one flows to RB. If you do the same calculation again, you'll see that the current that is flowing through IB will be the input current multiplied with RA divided by RA plus RB. So in this case, in the current divider, the current in the branch is proportional to the resistance of the opposite branch. So if you are trying to find out the current through RB, it will be proportional to RA. And intuitively, how can you say that that's true? You know that current always takes the path of least resistance. Wherever there is a lower resistance, more current will flow through it. So just assume that RA is very high and RB is very low. So let's just assume RA is 1 mega ohm and RB is equal to 1 ohms. So RA is much, much larger than RB. Because current takes the path of least resistance, in this case, most of the current will flow through RB, right? And almost no current will flow through RA. That sort of intuitively tells you that whatever the value of RA and RB is, the current flowing through them will be inversely proportional to it. If the value is lower, the current flowing through it will be larger. If the value is larger, the current flowing through it will be smaller. Right? And that makes sense intuitively, that because current will always take the path of lower resistance. Because it's a flow of electrons, eventually, current flow is a flow of electrons, and wherever you have lower resistance, the electrons will flow through that path. All right, so that's the basic of current division and voltage division. I wanted to talk about a little bit on amplifiers and their gains, because we'll be discussing about amplifiers a lot in this particular course. I think in 2 or 3 lectures, we'll be starting our discussions on op amps or operational amplifiers. So what does amplifiers do? If you have a small signal AC voltage input, amplifier's job is to increase that voltage amplitude. So if you have a very small AC input, the job of this amplifier is to make sure at the output you have a larger voltage swing. So let's say you have a 1 millivolt sine wave at its input. At the output, you are, let's say, expecting 10 millivolts of a sine wave or 100 millivolt of a sine. So the job of the amplifier is to amplify the input voltage. All right. Now, in this case, you are saying that there are multiple amplifiers. So let's say the first stage amplifier has a gain of A1. And the meaning of having a gain of A1 is basically this, that you have a 1 millivolt signal at the input. That's what I had drawn earlier, that you have a small sine wave at your input. And let's say at your output, you have a 10 millivolt voltage swing. So let's say this was 1 millivolt. From the peak to the trough, or from the highest point to the lowest point, you had 1 millivolt. And here from the highest point to the lowest point, let's say you have 10 millivolts. So what is the gain of the amplifier? The gain of the amplifier is the ratio of its output voltage swing to the input voltage swing. In this case, the gain is equal to 10, right? Because at your output, you have 10 millivolt, at your input, you had 1 millivolt. So the gain is equal to 10. If you had, let's say, 3 amplifiers cascaded, so what does this mean to have amplifiers cascaded with each other? This means you have one amplifier after another. So back to back, you have 3 amplifiers. And let's say the gain of the first one is 10, the second one is also 10, the third one is also 10. So what is the overall gain of these cascaded stages? So these are cascades of stages, and the overall gain will be a multiplication of all of these. Why? Again, just think about this intuitively. You had 1 millivolt input at the first amplifier. At the output of the first amplifier, you have 10 millivolt. Which means that at the input of the second amplifier, you have 10 millivolt. So at the output of the second amplifier, you'll have 100 millivolts, right? And that 100 millivolt is at the input of the third amplifier. So at the output of the third amplifier, you'll have 1000 millivolts, right? So you start with 1 millivolt and you end up with 1000 millivolts or 1 volt. How does that work? Because you have this multiplication in terms of the gain. So the first stage had a gain of 10, second stage had a gain of 10, third stage also had a gain of 10. So overall, you had a gain of 10 cube, which is equal to 1000. So we'll be using this property as well in our later lectures. So in this class, we are just trying to look at the fundamental properties or the fundamental theorems that you have in electrical circuit design, and we'll be using them in our later lectures. So the overall gain, in this case, if you write it in the form of mathematical equations. The gain A1, that's the first stage, will be equal to V1, that's the output voltage, divided by Vs, which is the input voltage. Now, one thing I would like to mention here and keep this in mind for the rest of the semester is that whenever we are talking about gain, we are talking about AC voltage gain. We are never talking about DC voltages. We'll come to DC voltages also when we discuss biasing and the need for biasing. But whenever you're talking about gain, it does not mean that you have a fixed DC voltage and you're increasing that DC voltage. It's not that. It's always AC voltage. You have a AC or alternating or basically a sine wave at the input, and at the output, you have a bigger sine wave. So that's all you are talking about. And the ratio of that bigger sine wave to the smaller sine wave is your AC voltage gain. Right? So you're not talking about anything related to DC. There are ways to increase the DC voltages as well. Those are called DC-DC converters, or basically DC amplifiers, that if you have a 1 millivolt fixed voltage or DC voltage, right? How can you make it 5 volts? So there are other circuits to do that. We'll not be discussing those in this particular course. So this course deals with AC input voltages, AC output voltages, and so on. But we'll also be discussing DC biasing of circuits and the need for DC biasing. And we'll show what is actually biasing and why do you really require it in the later lecture. So don't worry about it now. But for this particular lecture, keep in mind that whenever you're talking about gain in electronic circuit, you're talking about AC voltage gain or AC current gain, right? So you can write down these equations of A1, A2, and A3 in terms of the voltage divisions or the voltages. The first one is V1 over Vs, the second one is V2 over V1, and the third one is VO over V2. And then the overall gain is basically a multiplication of all of them. So these are again some of the, so we'll continue from here in the next lecture. But before we go there, I wanted to show you something. This is called Every Circuit. And I have also mentioned this in the syllabus. It's a fun tool to work with if you are just trying to look at, okay, what is happening if I'm dividing the voltage between two resistors? What is happening if I'm dividing the current between two parallel resistors, and so on. So you can create a free account here for students. You can create a free account. And then you can probably search for, let's say, for example, let me search for voltage division. And people have already created these many different circuits here, which they have placed. And I was looking at some of these circuits here. Let's see. Maybe this one. Okay, so what it does is that you see that there is a voltage source over here, which is 5 volts, and there is a 1 kilo ohm resistance connected to it. But there are these multiple switches which you can turn on and turn off to connect the other parts of the circuit to it. So for example, if I am, let me zoom out a little bit. Yeah, so you have this 5 volt source and then 1 kilo ohm resistance connected to it. Let's say you turn on this switch, which is connected to a 1 mega ohm resistance. So what it shows here is that how does the current flow from the voltage source through the 1 kilo ohm resistance, then through the 1 mega ohm resistance and to the ground. Now, because you have a 1 kilo ohm resistance here and 1 mega ohm resistance here, and the current that will be flowing through this path is basically 5 volt divided by 1 kilo ohm plus 1 mega ohm, right? That's what we learned through Ohm's law. Now, what is the voltage developed across the 1 mega ohm resistance? That is voltage. Maybe I can write that down. That input voltage multiplied with 1 mega ohm divided by 1 mega ohm plus 1 kilo ohm. Right? That's the exact equation that we learned in the class. That your voltage across one particular resistance is proportional to the value of that resistance. Now, 1 mega ohm divided by 1 mega ohm plus 1 kilo ohm is almost equal to 1. So this entire ratio is almost equal to 1. So your output voltage across the 5 volt or across the 1 mega ohm resistance, this voltage is equal to 5 volts. So that's what you see at the output on the top, that the voltage developed across this is 5 volts. Similarly, if you turn this switch off and turn this one on, you'll see that you'll have a 4 volt across this particular resistor. And that is because this is a 4 kilo ohm resistance, whereas the source resistance was 1 kilo ohm. So you have a ratio between 4 and 1, and then you divide the voltages as 4 volts and 1 volt. So just play around with these kind of circuits, you'll get a better feel of how the voltage division and current division works. And this is a tool we'll be using throughout the semester. Okay. Thanks, guys. We'll stop here. Let me know if you have any questions.